All right, so we're looking at another integration technique. These are in your IB formula booklet. So it's posted on Schoology, or I'll give you a copy. So take a look at them. IB uses arctan, arcsine, arccos. We tend to use in Canada inverse tan, inverse sine, inverse cos, that kind of thing, with the -1 representing inverse. So just realize that they are the same. So there's really no difference between these. Okay, the first row and the second row, and then we've added in a third one there. And I will need to check on the formula booklet. It might be included now. In any case, they're the same, and so we're just going to use them because they're in your formula booklet. But to start, we're just going to prove a couple of them. Okay, or actually, I guess those three. So it says use trig substitution and trig identities to prove the three formulas. So really, this is back into trig substitution. So we are going to, in this case, when it's a squared plus u squared, remember, we're not going to want to use sine or cos. It's not going to give us a Pythagorean identity. So we want to end up using tan. If you take a look back at the previous, from day 1 this year, I put them in there. So 1 plus tan squared is secant squared. 1 plus cotan squared is cosecant squared. So we want a 1 plus. And so I'm going to use tan substitution. So I'm going to let u equal, and square root of constant is a, so a tan theta, or you could use x if you wanted. So then du equals a, derivative of tan theta is secant squared. Okay, so then here we'll have a secant squared theta d theta over a squared plus a tan theta all squared. So then we get a secant squared theta over a squared plus a squared tan squared when we expand that out. So I'm going to factor out the a squared. I'm going to put the d theta at the end. Then a over a squared simplifies, right? So that's going to be 1 over a. I'll just put it out front. Secant squared theta. 1 plus tan squared is secant squared theta. Okay. So then that's going to equal 1 over a integral of d theta, which is theta. And then remember your substitution. So u equals a tan theta, so that means tan theta equals u over a. So tan is opposite over adjacent. And so here, well, actually, I guess I didn't even need a right triangle. So this will be 1 over a tan inverse u over a. Okay, and take a look back. That's what we're trying to prove, which is the right side. So this was the left side, it's the right side. Okay. Now we have an a squared minus a u squared, so now we can use sine or cos. I'm going to use sine, just because the derivative of sine is cos, so we don't have to deal with negatives. So I'm going to let u equals a sine theta. So du equals a cos theta d theta. So that's going to be a cos theta d theta. A squared minus a sine theta all squared. It out here, square root. So a squared 1 minus sine squared, kind of simplifying and factoring all in one step. So square root of a is a, and that's going to be the square root of 1 minus sine squared is cos squared. So the a's divide out. We get cos theta over cos theta, d theta. And then we get integral of d theta, which is theta plus c. And again, back to our substitution there. That means sine theta equals u over a. So theta would be inverse sine u over a. Okay, plus c. And then the third one. Okay, so again here we have u squared minus a squared. So we want to have, if you take a look back at your formula sheet, we want to have, you can either have a substitution where you get secant squared minus 1 or cosecant squared minus 1. I'm going to stick with getting secant squared, so I'm going to let u equal a secant theta. So du equals a tan squared, sorry, not tan squared, secant theta tan theta. Okay. So u is a secant, oh sorry, du is a secant theta tan theta d theta. U is a secant theta, square root, u squared minus a squared. Okay, well, you can divide those out right away. So tan theta, I'm going to put theta at the end. Then I'm going to have here a squared and then secant squared theta minus 1. Then we will have tan theta, root of a squared is a, root of, so then secant squared theta minus 1 is tan squared theta. Bring the 1 over a out, then we'll have tan theta over tan theta. And that's going to be equal to d theta, so 1 over a theta plus c. And then from here, secant theta equals u over a. So theta will be inverse secant u. Okay, expand this a little bit. So this will be 1 over a inverse secant of u over a plus c. Okay. All right, so now we're just going to use those. They're in your formula booklet. So we just proved them. Now we're going to use them. So what you want to note is if there's a coefficient with the squared variable, you want to get rid of it. Okay, so somehow, so here this is dx. So I don't want to have a 3x squared. So if I divide, basically I want to divide this by 3. So I want to multiply top and bottom by 1/3. Right? You have to treat each part of the fraction equally. Otherwise you're changing it. So that actually would be 1/3 here. And that would be 1/3 plus x squared. Okay? Still kind of yucky looking. So I'm going to bring that 1/3 in the numerator out. And then show it like this. And so now, look back at your formulas on the beginning part. Okay, so we've got 1/3 plus x squared. So we've got a number plus x squared. That's this one here. Okay, we have to take the root then of 1/3. Okay, so that's equal to 1 over a inverse arctan. So here, that means A will be 1 over root 3. Okay, we'll leave it unrationalized for right now. So that's A. And so we've got 1/3. This part here then, in that formula, says it's going to be 1 over A. You can see why. Don't rationalize it too soon. Maybe it'll simplify. And then tan inverse of x, whatever variable, over A. So when we do that, that ends up 1/3 root 3 tan inverse of root 3x. Oops. And so I would show that as root 3 over 3 tan inverse root 3x plus c, or you can use this as arctan. Okay. Next one doesn't have an x, it actually has e to the x. So you might want to do substitution to start. Let's let u equal e to the x. So du equals e to the x dx. So let's see what that is. So that's going to be u. Dx then, so it's going to be 1 over e to the x equals, sorry, just a sec. Actually, what am I doing? Okay, the next one, notice how it doesn't have just an x or just a variable like u or anything. It's got e to the x. So let's do a substitution and then see if we can do it. So let's let u equals e to the x. So du would be e to the x dx. So we can substitute that with du. So let's do that. So that's going to be, I'm going to leave it out front. And then inside, I'd have 1 minus. So e to the 2x is really u squared. Okay. So now we have a number minus u squared. Okay, so let's look back at the formula. So a number squared minus the variable squared. Okay, and we have that underneath the radical. Oops. Okay, so that's the second one there. So I'm going to, so basically our A is 1 in this case. Okay, and so when we take our, so it's going to be A, which is 1, which you don't even have to show, and then inverse of our variable, which is u in this case, over 1. Again, we'll simplify that because you don't have to show that. So this, then we just need to substitute back in because we need it in terms of x. So that's going to be inverse sine of e to the x plus c, or arc sine. Okay, and that's it. Oh, maybe in this last one here. There we go. Okay, and then this one is probably the third formula. All right, so we've got in the denominator x root of x squared minus 4. So let's look back here. U root of u squared minus number, so same form. Okay, so in this case, so our A is 2. So this is going to be equal to 1 over A, and then inverse secant of x over A. And that's really, you can just leave it like that. You can make your 1/2 a little smaller. But that's it. So we're done. So really in this, you're just using your formula sheet for these. Okay.